5, 4, 3, 2, 1. Engines full power and liftoff.
CRS-28 launched yesterday.
Okay.
And
Was it yesterday?
Yesterday it launched on the 5th.
Right. Okay.
And it had the final round of CCP on it.
So who was on that one then?
Concordia, along with a University of Montreal research as well. RadSat, I think, was on it. But yeah, so CCP is now wrapped up.
It's done.
I mean, maybe like we still have ops.
There's operations,
but
yeah.
CCP is no longer on the planet. Everything's in orbit.
LEO now, yeah.
Which is like so incredible.
It's amazing, you know.
I can't explain the feeling watching it was really weird. So deployment when those doors opened and our satellites like drifted off into space, it was it was so exciting. And I was like, okay, what now though? It was like yeah, now there's ops, but it was like it's gone. It's
all of that work is orbiting around Earth right now.
Yeah. Which is like incredible to actually think about. Like we touched the thing that's floating around Earth.
Well, you touched the thing. I didn't get the chance to touch it.
I mean, I touched it, but I didn't assemble it in the clean room.
I didn't even get to do that.
Right, you are.
I am very new.
Yeah, joined middle of AINT.
Yeah.
What a special time.
Yeah, that sounded quite stressful.
Yeah, I heard lots of horror stories, though. It's not going to happen for Cubics.
Nope, it can't.
Which I'm really excited for Cubics because it feels like a chance for us to do Exalta 2 just better.
Oh yeah, 100%. Where it's like a jumping off point from Exalta 2 is really what it is.
Yeah, like basically it's the same payload just for a different band and optimized to be more conservative, to be better in the where it was lacking last time.
Yeah, so on Exalta 2, we were originally going to fly the Electra board. That included a SWIR sensor and a veneer sensor, so shortwave infrared and visible near infrared. That got scrapped of fall 2021 because it was not possible in the timeline that we had. So we ended up flying a RGCam sensor that had a infrared filter on one of them and no infrared filter on the other one. So it is only measuring near infrared and visible light. There's no specific band in visible light. It's all visible light.
Oh, really? Interesting. Because the original plan was like more greenish wavelengths, I believe. Red?
Yeah.
I heard something about green as well. Oh, I'm just completely wrong.
We want green on Cubics mission.
Right. Okay. Sorry. But yeah, so you wanted to SWIR and red light.
Yep.
And then it just removed the filter, and now it's only all visible light.
All visible light and near infrared. There was no SWIR on Exalta 2.
I can't wait till we start getting some images because it's gonna be so like imagine seeing Earth from like an ISS orbit.
Oh, it's gonna be crazy.
I mean,
on something that we made in house.
Yeah.
Yeah.
It's going to be like a glorious day when we get our first image.
It will. And it's going to happen. It's got to happen.
Of course it's going to happen. I'm not even worried. But for Cubics, what do you think is going to be the biggest hurdle to get this next iteration going?
Time. It is 100% time. This year, or this mission is 2 years as opposed to the 5 years that we worked on Exalta 2 for. That's significantly shorter than, like, by 3 years. Like, we have 2 years to fully develop this payload. So, at certain points, you're like, okay, is this mission critical, or is this just a recommendation? Is this a requirement, or is this a recommendation? Right. So that's why we want to go with SWIR and green. And then, it'd be nice to have if we had near infrared and red. They're not mission critical. We still are able to image ice with SWIR and green. based on the normal difference snow index, or NDSI.
Maybe you don't have a good answer for this, but how difficult do you think it will be to double the amount of bands that we're imaging? So
It
go from
really
2 to 4.
comes down to filtering.
So do you want to describe what filtering is?
So all light travels in different wavelengths. Green is in the 550 to 600 range. Red is 650 to 700, I believe.
I think red is like 300 nanometers. Wait, no,
That's
sorry.
blue.
That's blue. Yeah,
Yeah.
I'm on the opposite side.
That is getting into UV.
Right.
But infrared, as you get into that range, you have quite the range. You go from 0.8 micron to 15 micron, which is a huge, huge range.
Mm-hmm.
So because the band in near infrared that we're shooting for is a 1 micron difference between the SWIR band, we're going to have to put 3 bands on one filter.
Right.
Right. So that makes the filtering harder. So there's different filtering techniques that you can use. There's bandpass filters, which pass through certain wavelengths of light that's specified on the data sheet. So those can be red, green, SWIR, or you could get a double one where it's got red and green, or green and near. And they actually also have triple band passes. So there's a green, red, and near infrared one. So with that, you can technically, onto a Bayer matrix, which is red, green, green, blue. So every other pixel is a green pixel.
I think you're over my head right now. So this filtering, kind of what is it doing? It's receiving a bunch of incident light from SWIR up to red or green is what we care about. And then how does the filter kind of sort that into the bands we want?
It literally will block.
Oh, it just blocks certain wavelengths?
Yeah.
Interesting.
Yeah. So that's a bandpass filter.
Mm-hmm.
Where I have a meeting actually set up in a couple of days to talk about butcher block filtering, which is where you literally chop up the sensor into different wavelengths of light. So certain pixels are only allowed to ever see red wavelengths. So if you divide the sensor into like pretty much 3, it depends on where the light is focusing on the sensor, but you just divide it into 3. We have 3 different wavelengths. So no other, it's directly on the filter, no other wavelengths will be able to incident onto the sensor.
Okay. Maybe this is a future consideration way down the line, but if you're taking an image and splitting it into 3 sections, which are each different colors, what kind of post-processing do you have to do to kind of stitch images together?
I'm not sure, to be honest with you.
I think Liam has dealt with that.
Yeah.
Maybe I'll ask him later.
It's probably something you can do in MATLAB. Just any sort of post-processing.
So I remember, oh my God, when was it? Maybe last fall or maybe last summer. It was right when ChatGPT came out. And Liam was writing the Iris post-processing code with ChatGPT. And he was like, I'm just going to test it and see how it runs. He put in this super long prompt about stitching images together and then filtering for green. And it gave him something that was kind of working.
Oh. So you just had to tweak it?
Yeah. It basically, he already had most of the post-processing code finished, but he compared it to what ChatGPT gave him, and they were pretty close to identical.
Wow, that is crazy.
So I like to say I'm a expert programmer now.
Right.
Because whenever I have a question, I just go to ChatGPT, and it basically works.
Yeah, as long as you're checking your work or its work.
Yeah, you can't rely on it.
You can't. It's great. It's a tool, but you're the one utilizing it, right? You got to make sure that it's doing correct work and that you're not relying on it, because like that's the last thing you want, is to rely on AI.
Yeah. So I've been trying to do a lot of research into like max Q and kind of how they determine that for like a rocket flight.
Right.
And I just like went to ChatGPT. I said, explain max Q to me. And it explained it backwards.
Oh, so it was the inverse.
It is like max Q is an effect due to increasing air density with altitude.
That's backwards.
That is backwards. Yeah. And then I was like, I think that's wrong. And it's like, sorry. And then it like rewrote it.
Yeah,
like,
you got to correct it sometimes.
Yeah.
Yeah.
So like, the only reason I knew it was wrong is because I have kind of experience with, I mean, I've done high altitude balloon tests where you can literally look at your data and the density is a straight line.
Yeah.
It just decreases with altitude. Like for that Canarock trip, we did 2 balloon missions.
Oh, really? I didn't know that.
Yeah,
That's
so we
awesome.
did one balloon mission the day before to like it's a part of their wind weighting program.
Okay.
So you kind of get a with the accelerometers and pressure sensors on board the chassis.
Right.
You can determine the air density, but also like any wind patterns in high atmosphere. Like
Oh, wow.
in the
Okay.
30-kilometer range. And so you do that the day before to kind of see weather patterns, and then you do that 20 minutes before your launch.
Oh, wow.
And that's part of their wind weighting program. And if they have to like put a hold on the launch, so they'll stop at T-15 and they'll ask for go. If at T-15 they put it on hold and they have to hold like an hour or two, like there's only like a certain band they're allowed to launch. So they'll hold like maybe an hour out of their 2-hour window.
Okay.
And then maybe launch another balloon to check the winds. And if it doesn't improve, then the launch would get scrubbed.
Right. Did that happen to you guys?
It got delayed 5 minutes.
Oh, okay. So nothing too crazy then.
Yeah, we also launched in 50-kilometer-per-hour winds. So
Oh, wow.
I don't know.
Wow. That is fast.
It was basically like standing in a tornado.
Yeah. Yeah. Jeez.
Like, well, you're on like northern Norway coast. So you have this, it's like open avenue to just like all the sea winds.
Pelted by the sea winds. Yeah.
Yeah. And like, I was actually honestly really surprised. We launched because like you're launching into a 50-kilometer-hour per wind,
And it just takes that thing.
and it's a ballistic rocket. There was no recovery on it.
It's like,
So it's like, really hope it doesn't land on
us. Yeah. Mhm.
I think it got 9K up. Like we had an apogee in 9.8K, and it went 9.2K out to sea, even into the like. So as a part of their wind weighting program, they changed the angle of the launch rail.
Oh,
So if like the wind speed increases, they'll decrease the launch angle
right.
to be more like
To calculate. Yeah.
Yeah. So you can actually get a lift effect shooting into the wind.
Oh, that's cool.
So like, yeah, it's this huge analytical process they have to do every 30 seconds during countdown to like finely tune for launch.
That is impressive. And that's all like remote control.
I mean, you have an operator, but
Right.
they have a bunch of software doing it.
Okay.
They also have a bunch of software making sure that no one is in the launch range, like in the danger zone. Like, because you're
Danger.
launching out into sea, right?
Yeah.
What if there's a Norwegian fisherman 2K out who's in the danger zone?
Yeah, that's not ideal. Hey?
So they have to like constantly check that. Excuse me. Constantly check that no one is in the
Danger zone.
yeah.
Can you imagine that? You're just out fishing. Some rocket just lands in the next to you. Like, that would be insane.
Like a student rocket, it would be like, oh, what was that? If one of the NASA sounding rockets went off, like you would retire.
You'd be like, someone's targeting ICBMs at me.
The Soviets are attacking. Actually, Andoya Space almost started World War III.
What?
Did I tell you this story?
No.
So they did a sounding rocket campaign. And like, don't think of the Mercator projection map. Like, we're a globe, right?
Mm-hmm.
So if you're in northern Norway, just over the North Pole is Russia.
Right.
They're neighbors.
Mm-hmm.
And we're shooting northeast. I mean, east doesn't really mean anything when you're that far north,
Yeah.
right? Like you're so close to the North Pole that north is almost like doesn't exist. But you're shooting towards Russia, and It was during the Cold War.
Oh,
Wait,
no.
was it the Cold War? I think, yeah, it was Cold War. They did a sounding rocket campaign, and they scared the Russian officials into almost declaring World War III because they thought it was an ICBM coming over the North Pole.
It's just a sounding rocket.
It was just, I mean,
just a sounding rocket.
they're pretty much the same thing. Like, you can take a ICBM, take the explosives out, put a payload in,
There you go.
and you have a sounding rocket.
It's a sounding rocket.
But yeah, it was quite interesting to learn about their history there, or they scared the Soviets to death.
That is crazy. I can't even imagine that.
We should. You want to do your certification test, right?
Like high explosives or the
High powered rocketry.
high power. Yeah, I do. Yeah.
Yeah, I want you to see a rocket launch, like one of those HPRs.
Oh yeah.
It is a different kind of feeling where you just watch all this work go Mach 1 in less than a second.
I really hope that I can go to Andoya. That's on my bucket list of my undergrad career.
For sure.
Yeah.
I will put a good word in for you.
I appreciate it. Thank you.
Like, do you know what is required to get your HPR Cert 1?
No, I don't. Do you?
Yes.
Tell me more.
Okay. So basically, the certification test consists of launching on a high-powered rocket with a certain motor.
Okay.
So Cert 1 is I can search this up, but I believe it's an IRJ sized motor.
Okay, that makes sense.
And in order to consider passing the test, you have to be able to recover it and immediately launch it. So the recovered rocket has to be in such a state where it could launch immediately again after a refuel.
Oh, okay.
Which, like, it sounds pretty easy, but they consider an unflyable rocket anything with like a fin damaged.
Oh.
So if your recovery is a little too weak, class 1 is H-class impulse. Class 2 is I-class. Sorry.
Okay.
So you would use a H-size impulse motor with this HPR that you develop.
Mm-hmm.
It would fly. You would then have to recover it with a recovery system, and they would have to be recovered in such a state that it can fly immediately again.
And you have to like send it off again?
No, you don't fly it again, but it has to
okay.
be in a state where it could.
Gotcha.
So all the fins have to be intact. All the pieces have to be together. Like, so you have it attached with shock cord. So when like it splits in half like an egg,
Yep.
and your recovery system comes out, you don't lose any piece.
It's all attached together.
And you need to have a GPS in it so that if it like goes over the horizon, you can still find it.
Oh, okay.
That's like part of being recoverable is it's
you just
locatable.
put an air tag in there?
Actually, I don't know if that's allowed or not. I'll have to check. But yeah, so that's basically what's entailed. And your class 2 and class 3 are the same thing, just with more propellant, like higher class motors.
Bigger explosions.
Yeah, and I really want to do it.
It goes up to 4, right?
There is a class 4, but it's a bit different. It's basically like equivalent to doing a SEDS project.
Oh, okay. That's a lot of work then.
And MCR, PDR, CDR, final report. That's all included in the class 4.
Wow. Okay, that makes sense. There's not a lot of people that go for that then, hey?
Yeah, and it's also quite expensive just to build a rocket.
Yeah, that's true. That would be a lot of money.
Though, like level 4, like you're in like class 4. So I'll actually pull up the rocket motor size thing.
Okay.
Our list. Because like a class O is basically all you need for any of your rocket needs. Like anything, class O is a total impulse of 40,000 Newton seconds.
Okay, that's a fair amount. That's a lot of impulse.
Yeah, amateurs really don't need anything more than that.
No, not at all.
Though you could, actually, I don't know if this is legal in Canada. I know it's legal in some states. Design a hybrid motor.
You could.
So, do you know what a hybrid motor is?
Yeah, either liquid fuel or solid fuel, and I guess oxidizer that's either liquid or.
Yeah, so you would have your propellant oxidizer pair. One of them's a fluid.
Yeah.
One of them's a solid. Usually you have a solid propellant liquid oxidizer, and you can get better performance out of it.
Okay.
Yeah, it's legal to make that in some states.
I've been looking into doing that for Star. I think that would be a really cool thing to bring to the university.
Yeah, I really want to do some kind of liquid propellant at U of A.
Mm-hmm.
Like, no one even needs to know about it. I just want to watch it. I just want to, even like a simple pressure fed bipropellant.
Yeah.
It would be incredible.
Oh, 100%.
Like, have you ever seen the videos of the Raptor test firing?
Yeah.
Blows me away every time.
Dude, I love the sound of the Raptor engine. I will literally, like, sometimes when I'm feeling sad, I'll be like, YouTube, show me Raptor test fire. And yeah, it brings me joy.
I agree.
It just sounds like hearing the roar of that is just, you can't beat it.
Yeah, what, 75,000 horsepower, something like that?
Something like that. That's a lot of horses.
A lot of horses
A lot of
under the
horses. A lot of horses crammed into that thing.
hood. But like, I know it's a bit arrogant to say, let's just make a liquid propellant system, an LRE. But it is something I really want to try.
Well, I mean, if it's a no-go from Star, I mean, it's something we can pursue on the side if we get a team of people. I'm not sure how it goes for forming a club, and I don't know if people are going to be like,
I don't think that could be a club.
Liquid Rocket Engines Design Club.
I don't think the U of A would want us with a bunch of explosives.
Well, Hyperloop exists.
Do they have explosives?
No, but Hyperloop.
They don't care if you're a club and not threatening the campus, but as soon as you have to store enough propellant to take out, like flatten a building, some questions are raised.
Well, UBC does it.
Do they?
UBC has their Blackcomb hybrid rocket engine, and UFC is also working on, I think, either hybrid or liquid. Or maybe Blackcomb is.
I didn't know
fully
UFC.
liquid.
Oh, they have UFC has a propulsion class.
Oh, that's cool.
I'm transferring. I'm kidding.
Sorry, U of A. That
I know I graduate soon, but see ya. I know UFC just did a static fire of a rocket,
yeah.
though I think it was a pressure fed system. So I guess UFC does allow you to. Oh no, maybe we have to actually ask an advisor for this.
Oh, 100%. I wonder who we should talk to. That. Well, we'll talk about it after, but let's make it happen.
I agree. Funding might be an issue.
Oh,
Storage is definitely going to be an issue.
funding, storage, all of the above will be an issue, but
Pundeep actually wants to make a pressure fed system too.
okay. So we got
We
got
3.
you, me, Pundeep, and
Andre
And
would, Andre would be there in a second.
okay, we got Andre. We can talk. I think Kirtan would totally.
Kirtan would probably help us. Yeah.
Yeah.
I solved our funding issue. I'll tell you after, so I don't spill our secrets.
Good plan. I like that.
What do you think is the biggest shock to come from working on nano-satellites?
Just
Like, let me tell you my personal one. So, I second year me, bright-eyed,
Yep.
joins AlbertaSat, and for the next year, because it was COVID, everything was online. I've seen CAD of our satellite, but I never like checked dimensions or even knew kind of the size of this thing. And when I saw it in person for the first time, and it's the size of a bread loaf, that was my biggest shock. I'm like, what? This is our satellite?
It's crazy.
This
You don't
thing's
realize
gonna
how small
monitor wildfires? So yeah, it kind of caught me off guard. And did you have something like that when you started working on it?
I kind of had a frame of reference for how small it was going to be when I was doing my KOP kickoff project, because you got to make like a CubeSAT structure.
Did you did the mechanical
I
KOP?
did. Yeah.
I did that too, but I still didn't.
You didn't clue into how small it was?
I guess I was just really naive.
That's
I
fair.
was living in my own world. But like the CubeSat structure itself, like I what university was it? Was it Manitoba Sat? We were looking at their website, and they describe their mechanical structure, and it's like, roll, be a box.
Yeah, be a good box.
Be a
is what it
good
was.
box. Yeah.
Yeah.
But like, that's essentially what you're designing. Though, like on the surface, it's just make a bunch of metal in the shape of a box and fasten it together. But it is actually like a lot. What would you call it? It goes a lot deeper than that. So, like, for example, if you want to use nanoracks as a deployer,
Right.
you must have a surface hardness greater or equal to anodized 6061 aluminum.
Which is why we used anodized 6060 aluminum.
Yeah.
Or did we use 6061?
We use 6061.
Okay.
But like in the act of fulfilling that requirement,
Right.
we ended up messing up other requirements.
Such as
This CubeSat must have a common ground.
common. Oh.
So
Okay.
the whole
Everything's-
structure has to be conductive,
Okay.
such as to form a common ground. So in the we anodized our rails so that the rails were a certain hardness that match anodized 6061 aluminum, and then we anodized the rails and they were no longer conductive, so we no longer had a common ground.
Yeah.
So then we had to remove the anodization to restore the common ground.
That's why they removed the anodization. That makes sense. Okay.
It's not a good feeling when you have to bring like a file and sandpaper to your
CubeSat
to your
structure.
CubeSat.
Yeah, that's not ideal.
We're not doing it for cubics, or at least not that way. We're gonna do something unique.
Cool. Cool stuff. Just, go to a couple micron, or not micron. That would be insane. If you could do a couple micron on the lathe.
Yeah, you have some real you should be a doctor if you can get that kind of precision.
Yeah. You could take a thou off that and
Though
there you go.
you just did all your manual training, right?
mm-hmm.
How was that? Like I've actually never done any metal lathe work before. I've done CNC, but I haven't done any manual milling.
It's completely different to CNC. You're cranking everything by hand, so it's all by eye when you're finding surfaces.
Mm-hmm.
So if you mess up a tiny bit, your part's gonna be off by a couple thou.
Right.
So a thousandth of an inch is what thou means. So you gotta be you gotta walk it in very, very slow. There's a lot of backlash in the handles. So these machines have been used for tens, maybe 20s of years. They've been used and abused. So sometimes the mechanical parts don't mesh right away, and that's what you call backlash. And when you're in that area, you're not going to get a super accurate measurement. So you have to walk it in from a reasonable distance, and then bring it down, and then you got to touch off on the surface just enough that you can see a little bit of material coming off, and that's how you know you're at zero. And from there, you can zero out on a digital readout, and then you can go down the depth or the width, whatever you need. And it's similar with the lathe. You have to touch off on the surface, then zero out, and then, the digital readout as you move along shows you how much you've moved along. Yeah, it's different. It's a lot of you got to be paying attention. You with CNC, you just let the thing go.
Yeah. Though, where we do our CNC, you're supposed to babysit it the whole time. So every time a tool changes, you got to go in there and
make sure it's changing. Yeah.
Yeah. But still, it's such a good feeling. You just make your tool paths, press play, and you have a part.
Well, you're not stressing that you're gonna mess something up.
Yeah, that is fair. And you also have a certain degree of confidence that you're actually machining to a certain tolerance.
Oh, 100%.
And you're not going to end up with something completely different. Though when I did my training, my chamfer, when you work with metal,
Yep.
you end up burring sharp edges.
Yes.
And so what you'll do is you'll run a chamfer around at the end to deburr it.
Right.
And for some reason, my work coordinate system for my CNC training was just a little skewed. And so when it did the chamfer, it basically did a full chamfer, 2 mils large on one side and maybe a tenth of a mil on the other side.
That is
so it was
tragic.
completely off by a mil and a half.
Right.
But other than that, it was pretty pretty precise.
Well, and the nice thing about that is you can just put another block of material on, change your axis or whatever, and you're set.
Yeah.
I mean, that's expensive, obviously. That's an expensive mistake when you're working with, big things like that. But
Aluminum is actually a lot cheaper than I thought.
it is. Aluminum extrusion is cheaper than I thought it was going to be, to be honest with you.
Like for Kenner GX?
Yeah, for
like
Kenner GX.
Oh, what are the Bosks?
The Bosks?
Like the Bosk extrusions, right?
Yeah.
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 I looked into it. A 6-inch diameter circular stock that is 10 inches long is like $114.
10 inches long.
Yeah. So what? Like that
Yeah.
by that?
Oh, okay. Yeah.
Of solid aluminum?
That's pretty solid.
Well, I thought it was going to be like 500.
Yeah. Metal's expensive. I mean, it makes sense.
So I think my plan is just to get a huge circular bar of aluminum and then just cold cut all the like pizza slices I need. Because I do have to make a copy of our CubeSAT structure.
Oh. Okay. Are you going to do that in the garage?
Yeah.
We can do that in the garage?
I have people seem to doubt me, and maybe I'm just like completely wrong. I think I have a manufacturing plan.
All right.
Like on paper, it works.
On paper, it works, yes.
And the garage told me I can do all the sketchy stuff it requires to make it work. I asked for permission instead of forgiveness.
Please, can we use the machines to do sketchy things?
Like, it's not that sketchy, but like the work holding for the rails are not ideal, to put it lightly.
Oh, boy.
So I have to kind of like jerry-rig a work holding solution.
Well, I mean,
Do you ever...
it's engineering.
This is
Sometimes
a tangent. Do you ever watch like BPS Space?
I have watched
Have you-
like I haven't watched him in like 3 years, but
Okay. He's releasing currently like a series of videos about making a solid rocket motor.
okay.
And he released like one yesterday
Right.
about making the top plate of his motor. And so like that's milling a circular plate with a bunch of O-rings on it
Okay.
and a igniter nut or igniter bolt. He talks about all that process. But he literally does a work hold solution by taping it to his CNC.
Wow.
Like,
You don't have to do that or do you?
no, I won't have to do
Oh,
that.
okay. Okay.
But
Good.
I was watching it, and then he's like, yeah, this is not the proper work holding solution, but I better not hear about this in the comments. And it's literally him just taping it onto the
Oh,
CNC.
that's funny.
It's not going to be anything that sketchy.
Okay. Good. Good. We're not. We should use like a proper way to CNC for the actual structure, though. Just saying now, like.
Well, just like they're so long and thin, where
Yeah.
you run into issues with normal work holding. Because if you use like I think they're 5-inch long jaws.
Okay.
If you use 5-inch long jaws, then your part overhangs by 7 inches.
Okay. Yeah. That's.
And when your chip load is too great, you end up machining. Like if you machine on the overhang, you'll end up like your
warping.
chip load will warp the part. And
Okay.
your tolerances will be all over the place.
Yeah, that's not what you want.
So blue tape actually is a good solution.
I'll keep that in mind.
Yeah. If you ever need really sketchy CNC practices, I
Blue
got
tape.
blue tape. And I got plenty more for you.
He's got a whole list on his phone. Pull it up.
Well, one of them involves putting a work holding in a work holding. But
Hey, that's a valid thing. Like they put chucks and chucks down in the machine shops.
do they really?
Yeah.
I'm talking about like vices and vices, but yeah, chucks and chucks.
Same thing. Yeah, literally. Like Ben was asking about it and he's like, yeah, we do that. Yeah.
Maybe we should machine in the physics shop. If you're allowed to do sketchy stuff there.
Well, we are not allowed. The machinists can do it because they have years of experience.
How can I get a 2-year diploma in 2 months?
Cram.
Okay, I'm
Yeah.
on it.
Just grind. It's grind time.
All right. You know, you're such a blast to talk with.
It's been an honor.
All right.
You're my favorite voice to hear over these headphones.
Aw, don't make me blush. Thank you for listening. We will be back next week.
All right. See you, everyone.
Peace out, Space Cadets.